There is a power inverter somewhere in the world right now running too hot. Not because it was built wrong, because the material it is made from has a hard limit baked into its physics, and we are pushing up against that limit everywhere, all at once. In electric vehicles, in data centers, in the solar farms trying to power the grid. Silicon is failing us, not slowly, not in theory. Right now, at scale, there is another material. It has been sitting in research labs since the 1980s. It outperforms silicon by every measure that matters. No one has been able to build it cheaply enough to use, until a chemist in Houston ran electricity through a pile of coal dust and got diamond. 1 billion years, compressed into a second, no furnace, no pressure, no existing diamond, in under a second. To understand why silicon fails and why diamond does not, you need to understand a property called the band gap. Every semiconductor has one. It is the energy gap between electrons that are locked to atoms and electrons that are free to move and carry current. A wider band gap means a material can handle higher voltages and higher temperatures before breaking down. Silicon's band gap is narrow. That is why it works well for low power computing and why it fails when you push it hard. Engineers found a partial fix. Materials called wide band gap semiconductors, silicon carbide and gallium nitride, handle more heat and more voltage than silicon. Silicon carbide is already inside Tesla's drive inverters. Gallium nitride is in the fast chargers for your laptop. Both represent real, meaningful progress, but they are not enough for what is coming. The next generation of power systems, ultra-high voltage grid switching, electronics that need to survive in space or in a jet engine, and pulsed power for the most demanding military and scientific applications need something that silicon carbide and gallium nitride simply cannot deliver. For 40 years, one material has existed that could handle all of it: diamond. Silicon's band gap is 1.1 electron volts. Silicon carbide's band gap is approximately 3.3 electron volts. The exact figure varies by crystal structure, but it is roughly 3 times wider than silicon's, which is why it survives conditions that destroy silicon. Diamond's band gap is 5.5 electron volts, 5 times wider than silicon, nearly twice as wide as silicon carbide. That puts diamond in a completely different operating regime. Its breakdown voltage, the point at which the electric field tears electrons loose and destroys the device, is conservatively 30 times higher than silicon's in practical device comparisons. And at the material level, the gap is far larger. It is roughly 3 times higher than silicon carbide's, and it has the highest thermal conductivity of any natural material, higher than copper and higher than silver. What that means in practice: a diamond transistor doing the same job as a silicon carbide transistor can be made significantly smaller, run at far higher voltages, generate less waste heat, and survive conditions that would destroy everything else. In every category that matters for power electronics, diamond outperforms by multiples, not margins. Scientists have known this since the 1980s. They have been trying to build diamond electronics ever since. The material is extraordinary. The problem has always been the same: no one could manufacture it at a cost that made any industrial sense. 2 methods dominated diamond synthesis for over a century. Both worked. Neither was practical. High pressure, high temperature synthesis, HPHT, is how most industrial diamonds are made. Carbon, a metallic catalyst, 50,000 atmospheres, 1,400 degrees Celsius. Days rather than millennia. Real diamond comes out, but with metallic inclusions from the catalyst embedded in the crystal. For a cutting tool, that does not matter. For a transistor, it is fatal. You cannot build a power device from HPHT diamond. Chemical vapor deposition, CVD, solves the purity problem. A seed crystal goes into a vacuum chamber. A carbon containing gas and a large excess of hydrogen are introduced, and microwave energy creates a plasma hovering just above the seed surface. Carbon radicals rain down, bonding either in the diamond arrangement or the graphite arrangement. Atomic hydrogen continuously etches away any graphite that forms while leaving diamond untouched, selectively removing the wrong structure while preserving the right one. The result is a surface that can only grow in the diamond direction, layer by layer, over days and weeks, producing crystals that are exceptionally pure and genuinely usable for electronic devices. Researchers at the University of Illinois have used CVD diamond to build power devices handling thousands of volts, several times the maximum silicon can manage. That is not a marginal improvement, that is a different class of device entirely. But the economics are brutal. A 2-inch CVD diamond wafer takes weeks to grow. It needs reactors costing hundreds of thousands of dollars, and conditions controlled to extremely tight tolerances, a temperature fluctuation of a few degrees, a trace of the wrong contaminant, and the entire crystal is ruined. A silicon wafer costs a few $100s. A comparable CVD diamond wafer costs tens of thousands of dollars. And unlike silicon, that price has not dropped because the fundamental throughput of the process, weeks per wafer, has not changed. And even if you solve that, there is a second problem. To grow CVD diamond, you need diamond to start with. A seed crystal, good diamond to make good diamond. Every facility producing CVD diamond for semiconductors has to source its seeds from another CVD facility, which got its seeds from yet another. The supply chain is circular and expensive at every link. There is no cheap entry point, there never has been. That gap between what diamond can do and what it costs to make is the wall that has kept diamond out of electronics since the 1980s. They called it the ultimate semiconductor back then. They still call it that today. The problem has always been manufacturing. To understand what the solution required, you first need to understand why the same element can be both graphite and diamond. Both are pure carbon. The difference between them, the entire difference between something that crumbles in your fingers and something that can cut through steel, is purely geometry. In graphite, carbon atoms sit in flat hexagonal sheets. Those sheets are held together by weak intermolecular forces rather than chemical bonds, which is why graphite is soft, why it is slippery, and why it leaves a mark when you drag it across paper. In diamond, each carbon atom bonds to 4 neighbours in 3-dimensional space, pointing toward the corners of a tetrahedron. Every carbon is locked to 4 others, those 4 locked to 4 more, extending in all directions without a single weak link. No layers to slide, no planes to shear, just an unbroken 3-dimensional lattice that is, at the atomic level, as strong as chemistry gets. That geometry is why diamond is the hardest natural substance on Earth. It is why it conducts heat so extraordinarily well. The rigid lattice transmits vibrations which carry heat faster than almost anything else, and it is why diamond's electronic properties are what they are. The same strong, stable bonds that make it hard also create that enormous band gap and extraordinary breakdown voltage. Same atoms, completely different structure. One writes on paper, the other stops bullets. Building diamond under natural conditions requires enormous pressure and heat sustained over geological time, which is why nature does not do it quickly. James Tour is a chemist at Rice University in Houston, one of the most cited researchers in his field, and the founder of a company already commercializing a related process for graphene production at industrial scale. His lab had been running flash Joule heating experiments since around 2020. A large reservoir of stored electrical charge, a capacitor bank, is connected to a sample of carbon through electrodes. When it discharges, current surges through the carbon. The carbon resists that current, and resistance converts electrical energy into heat, not gradually, the way a space heater warms a room, but instantaneously. The entire energy of the capacitor dumps into the sample in a flash, driving the temperature to over 3,000 degrees Celsius in milliseconds. A billion years of pressure and heat, compressed into a fraction of a second. At that temperature, iron does not melt, it boils. In 2020, in the journal Nature, Tour's lab showed that this flash could turn carbon from almost any source, including coal, food waste, and plastic, into graphene in under a second. No furnace, no reactor, no solvents, just electricity. A year later, they went further. When you add a small amount of fluorine compounds to the carbon before the flash, something different happens. At those extreme temperatures, carbon atoms briefly reach a state where the diamond lattice bonding structure becomes energetically favourable. Normally, when the material cools, carbon settles back into graphite, the stable form at room temperature. But the fluorine compounds bond to the surface of the forming diamond nuclei and act as chemical scaffolding, holding the tetrahedral structure in place long enough for it to lock permanently as the temperature drops. Without the fluorine, you get hot carbon. With the fluorine, you get diamond. The result is nanodiamond, crystals measured in nanometers. Not gem diamond, not the large single crystals that chemical vapor deposition produces, but diamond in every chemically meaningful sense. The same carbon-to-carbon bonding, the same tetrahedral lattice, the same crystal structure that gives diamond every property that makes it remarkable. A 2025 paper in ACS Nano, building on that 2021 work, and in collaboration with Xi'an Jiaotong University, demonstrated this using coal coke as the feedstock. After removing non-diamond carbon, the nanodiamonds reached very high purity and showed thermal stability comparable to commercially produced nanodiamonds made by conventional methods. And, critically, those nanodiamonds were then used as seed crystals to grow higher quality diamond films via chemical vapor deposition, CVD, at bench scale, in a laboratory, but the principle is established. Waste carbon turned into diamond by electricity, the seed that starts the entire diamond semiconductor supply chain. Remember the circular problem. Diamond needs diamond to start. Flash-produced nanodiamonds break that loop entirely. If waste carbon and electricity can produce seed crystals at low cost and high volume, the economics of the entire chemical vapor deposition process change. You no longer need expensive diamond to start. The input and material costs almost nothing, and flash Joule heating uses a fraction of the energy of any conventional synthesis method. The feedstock is carbon waste, things people pay to get rid of. Think about what that does to the research landscape. Sourcing high-quality CVD diamond seed crystals can cost many thousands of dollars before a lab has grown a single device. That price keeps most research groups out entirely. Cheap seeds produced from waste remove that barrier, and more labs working on diamond simultaneously means faster progress on every downstream problem. There is one more potential advantage, one that connects directly to what has historically been the deepest unsolved problem in diamond electronics. In chemical vapor deposition, doping, which means adding atoms like boron or phosphorus to control a semiconductor's electrical behavior, is a separate, carefully controlled step. To build a transistor, you need two complementary types of material, p-type, which conducts through positive charge carriers, and n-type, which conducts through electrons. Without both, you cannot build the complementary pairs that make logic and power switching possible. P-type diamond, made by incorporating boron, is achievable. It works. N-type diamond is a different story. The natural candidate is phosphorus, but phosphorus atoms are significantly larger than carbon atoms. Incorporating them into the diamond lattice during chemical vapor deposition growth introduces strain that creates defects severe enough to undermine the properties that make diamond worth using. This is the problem that stalled the entire field in the 1990s, and why silicon carbide captured markets that diamond was supposed to own. Progress has been made since, but N-type diamond remains significantly harder than P-type, and the gap between laboratory demonstration and reliable manufacturing is still wide. During the flash, dopant atoms mixed into the feedstock can potentially be incorporated into the forming crystal as it nucleates rather than being added afterward into an already growing lattice. Whether the chaotic millisecond timescale conditions of the flash produce doping uniform enough to be useful is an open question that the published research has not yet answered. But if it works, it sidesteps one of diamond electronics' deepest obstacles in a single operation. You are not just making diamond, you are potentially creating the starting point of an entirely new supply chain and touching the hardest unsolved problem in diamond electronics at the same time. 3 real obstacles stand between where this is now and where it needs to be, and none of them should be minimized. The first is crystal quality. Flash Joule heating produces genuine diamond lattice crystals, but they are small. variable in size, and far from the structural perfection semiconductor manufacturing requires. In silicon, modern manufacturing has reduced defect densities to extraordinarily low levels. Diamond is far harder to grow at that quality, and the demands are higher because diamond devices operate at voltages where a single defect can be catastrophic. A device rated for 5,000 volts might fail at 3,000 volts because of a single defect in the seed it was grown from, creating a local field concentration that tears the material apart before the bulk crystal would be stressed at all. Defects in seeds propagate into chemical vapor deposition crystals, and defects in those crystals propagate into devices. Using flash nanodiamonds is a step toward breaking the supply chain problem. It is not yet a step toward the crystal quality that semiconductor manufacturing ultimately requires. The second is process control. The flash happens in under a second at temperatures exceeding 3,000 degrees Celsius. Every variable, flash duration, current density, fluorine concentration, feedstock composition, cooling rate must be controlled with precision across every single batch. Tor's lab has continued to refine the flash Joule heating platform. A related paper in Nature Chemistry in August 2024 demonstrated gram-scale synthesis of more than 20 distinct solid-state materials using a Joule reactor variant of the technique, evidence that the underlying process is becoming more controllable and generalizable. But a process that produces good nanodiamond 90% of the time is a serious problem in an industry where a single contaminated batch can propagate defects through thousands of downstream devices. The third is the path from seed crystal to finished device. Even if flash nanodiamonds become reliable chemical vapor deposition seeds, the downstream infrastructure does not exist at scale. Diamond etching is genuinely difficult. The same hardness that makes diamond remarkable also makes it resistant to the patterning processes used on silicon and silicon carbide. Electrical contacts require surface chemistries that are still being worked out. N-type doping remains a manufacturing challenge, and all of it has to be qualified against the reliability standards of real power electronics, a decade or more of thermal cycles and voltage transients without failure. These obstacles are real. They are not fatal. The chemistry works, the nanodiamonds form, the seed crystals grow, the films deposit, the devices operate. What doesn't exist yet is the industrial infrastructure that turns a working lab result into something an engineer can order from a catalogue and trust for the next 15 years. Building that is a decade of work, at minimum. But the same was true of silicon carbide, and silicon carbide is now in every serious electric vehicle on the road. All of that matters because of what electricity has become. Power electronics are the semiconductors that convert and control electricity in everything from phone chargers to wind turbines. Every time electricity moves from one voltage to another, from solar panel to grid, from grid to motor, from motor back to grid during regenerative braking, a power electronic device performs that conversion, and every conversion loses energy as heat. Those losses add up. A modern inverter converting solar power to grid electricity might run at 97 or 98% efficiency. That sounds excellent, until you consider the scale. Global electricity consumption crossed 30,000 terawatt hours in 2024 and is rising fast. Industry projections suggest power electronics will handle upward of 80% of all electricity consumed globally by 2030 as electrification accelerates. At that scale, the 2 or 3% thrown off as heat across every electrical conversion happening on the planet at every moment represents hundreds of terawatt hours annually, entire power plants generating electricity that exists only to be wasted. Diamond changes that arithmetic. A diamond transistor loses less energy at each switching event because it switches faster and at higher voltages without resistive losses eating into efficiency. The same conversion a silicon device does at 97%, but a diamond device could do at 99 or 99.5%. At global scale, the difference between those numbers is staggering. In electric vehicles, the drive inverter is one of the largest and heaviest components in the drivetrain after the battery. Diamond would shrink it further than silicon carbide already has, and potentially eliminate liquid cooling entirely because lower switching losses combined with diamond's extraordinary thermal conductivity means the device simply does not get as hot doing the same job. Lighter, smaller, more range per charge. In data centers, a significant portion of energy consumption goes not into computing, but into power conversion and cooling. Diamond power electronics would cut both simultaneously. In the power grid, high-voltage direct current transmission is critical for moving renewable energy from where it is generated to where it is needed. The converter stations that make HVDC work are among the most expensive pieces of electrical infrastructure on the planet. Diamond switches capable of handling those extreme voltages would make them smaller, cheaper, and more efficient. Governments are starting to place bets on exactly this. ARPAE, the US government's advanced energy research agency that funds high-risk, high-reward energy technology at the earliest stages, has committed $42 million across 15 projects targeting next-generation power semiconductors for grid applications, including diamond devices at the University of Illinois, that have already demonstrated breakdown voltages several times higher than the best silicon can manage. Diamond was identified as the ultimate semiconductor in the 1980s. Researchers spent the 1990s convinced chemical vapor deposition diamond would change everything within a decade. It did not. The N-type doping problem proved harder than expected. Competing materials made faster progress, funding dried up. By the early 2000s, it had become a cautionary tale, always 20 years away. It was the same thing people used to say about fusion, and then another 20 years passed and it was still 20 years away. The revival started around 2010, as researchers realised silicon carbide and gallium nitride were approaching their own ceilings. The most demanding future applications needed something beyond what even wide bandgap materials could offer. Diamond was back in the conversation. By the early 2020s, working devices with breakdown voltages in the thousands of volts were being demonstrated in laboratories. ARPAE launched its ultra-fast program specifically to accelerate the timeline. Then a chemist in Houston who had spent years studying what electricity does to carbon found that a millisecond of current can force the structure that nature takes millions of years to build, starting from coal coke, from plastic, from food waste, with no industrial setup, no extreme pressure systems, no existing diamond required. Silicon carbide went through the same long development arc. Researchers demonstrated its advantages over silicon in the 1980s. It took roughly 2 decades of grinding work before the first commercial devices appeared, and within a decade after that they made it into electric vehicles at scale. The path was long, the destination was reached. Diamond is on the same road, earlier on it, but on it. We have spent a century treating carbon as something to burn, bury, or throw away. It might be the seed of the most powerful semiconductor we have ever found.